I'm just gonna start recording. Okay, cool. So, hi, my name is Tyla, and I'm a senior, and I've been in robotics for 4 years. I'm currently the lead CAD of Blood, Sweat, and Gears. I also do a little bit of everything, so I dabble in programming and build as well. But this year, since CAD is actually very important this year, since we can't really build robots in real life, I decided to kind of focus more on the CAD aspect of things. So basically, this presentation is about FTC design, as well as a little bit of CAD. I wanted to focus on FTC design first, because you can't just focus on CAD purely, because CAD is used as a design tool, rather than, it's just a tool to aid you in designing your robot. You need to know how to design in order to CAD, so yeah, that's just how it works. That's how it makes sense. So yeah, next slide. The engineering design process. So this is important because in real life, in the industry, in the engineering industry, the actual professionals use this design process to carry out their work. It's also important to follow this as a team, because judges are actually looking for this in your engineering notebook, as well as they may ask you during judging if you follow a process or how you guys came up with your designs and whatnot. So this is kind of a fundamental. So the first step of the engineering design process is defining the problem. So in the real world, engineers basically solve problems by making things. So yeah, they're defining the problem. However, we're not really solving the world's problems here. We're just playing a game. This is just a robotics competition. So our problem is actually just the game, which is ultimate goal, obviously. The second step of the engineering design process is doing background research. So this is important because you need to fully understand the problem you're trying to solve. So in this case, reading the game manual is fully understanding the game, making sure you know what is and what isn't allowed to do. Basically, the game manual. Background research also includes learning different types of mechanisms. So there's different ways of approaching building a robot, and there's popular different types of mechanisms, basically. So just having the knowledge in your head just allows you to have ideas of, oh, how can I apply this mechanism for this game? So it's just kind of good to have that knowledge. The last point I have, I should use a pointer. The last thing I have that's very important is looking for similarities from past seasons. So first, likes to reuse game elements from past years, as well as reusing game concepts, okay? So 4 years ago, there was a game called Velocity Vortex, and it was a shooting/launching game. This year is also a shooting/launching game, so you might want to look at robots from Velocity Vortex and want to look at videos to get an idea of what they use, so you can incorporate that into the game we're playing this year. So yeah, okay, third step is specifying requirements. So obviously you can't just make whatever you want. You can't have a flying robot, obviously. So there's always some limitations when it comes to engineering. So in this case, every robot must fit within the 18 by 18 by 18 inch sizing cube. That's just kind of the size you're only allowed to be, you're allowed to fit within. Weight. Weight is crossed out because it's actually not a requirement this year. It was in past years, but just so you know, it used to be a requirement. It's not this year. You can only use 8 motors and 12 servos. Pretty self-explanatory. And your strategy. So sometimes your strategy might be a limitation, right? So this year you could shoot, but there's also the option of going for the lower goal. Okay, maybe your team is afraid of shooting, or everyone should try to strive for shooting. However, if you feel like, oh, it's not feasible, I don't think we can do it within this amount of time, we're just gonna go for the low goal. So that's a limitation you guys set for yourselves. So your robot is going to look different because you decided to not shoot. You're going for the low goal. So yeah, that's kind of a limitation you could have. There's many others, but I just went over some basics. So yeah, fourth step, brainstorming, evaluating, and choosing a solution. So basically, this is just sketching and CADing your design ideas, just different ideas. Try to get as many as possible, and yeah, that's pretty much all for that step. Developing and prototyping a solution. So this is where you actually start to build your ideas in real life. Obviously, we can't really do that this year. I'm not sure if we are going to be able to. I think Santana and Mac were thinking of letting us take parts home, but that's not confirmed yet. But yeah, ideally you would build whatever you came up with, and then this goes into the next step is testing what you built. Pretty obvious. You just test, see if it worked the way you wanted it to. Did it break? Did it not break? You know. Yeah. Okay. This step, solution meets requirements. Yeah. This is kind of combines these two steps. How well did it work? You know. Does it meet criteria that you guys set? Or yeah, yeah. The last one says communicate. Yeah, communicate results. So that's also kind of self-explanatory. These are kind of all combined. Basically, you just discuss with your team which prototype you think worked the best and which one you guys actually want to use for your robot. Given you would have multiple different prototypes at hand. So yeah, that's it for this slide. So how to get the hang of FTC robot design. So as a rookie, I've experienced this myself when I was new. It's kind of hard to come up with ideas simply because you don't know what to expect. You've never seen anything before. You don't know what to base your designs off of. You know, you just kind of have a blank slate and you don't know where to start. So my number one recommendation for getting a feel for robot designs and you know, the different mechanisms is by watching robot reveal videos from past seasons. So yeah, you can kind of see a pattern between the different types of mechanisms that are used, and you could basically tell that they're all similar in a way depending on the game that you saw. Yeah, like I said earlier, Velocity Vortex 4 years ago was a shooting game, so you should look at Velocity Vortex videos. Yeah. Okay, at this point, I'd like to specify or go into is that I hate to say this, but innovation is rare. Okay, chances are you're not going to come up with something that someone hasn't already thought of. So yeah, there's also that thing where innovation could sometimes not be the best the best thing to go for, right? It comes with a certain risk, okay? Because if the thing you came up with was super innovative, that no one has done it before, there's always that risk of it's never worked before. You don't know if it's ever worked before. It's just kind of risky. However, if you can execute it well, then that's great. Then you did it. That's amazing. So I'd like to just show some videos of where innovation was actually it actually was very effective and it worked. So let's do that real quick. Why is it being weird? Bruh. Hold on. I broke it. Please work. Stop it there. And did someone say something in the chat? I heard it.
He just said he wished you could hear the video.
Oh yeah, the music is epic. But yeah, no. Okay, so yeah, as you can as you saw, they used like it looked like an accordion, right? Like I've never seen anyone do this before. This is like crazy. I have no idea how they were able to pull it off, but they managed to do so. Okay, this team is like crazy. They're insane. I don't know how they have the skills to do this. I don't know how they came up with it, but it was very effective and they were able to pull it off very well. So yeah, here's an example of ineffective innovation. Keep in mind, this was just a concept. This is the same team. They just did this for fun, but yeah, I'm just gonna show you. Okay, I'll stop it there. You guys get the idea, right? So instead of wheels, they decided to use balls, which is kind of interesting. However, I mean, obviously it's not, attached to anything. It's not a full-fledged robot. But I do see there could be a lot of issues associated with this, right? So personally, I see it as too bulky, right? Most of the space is being taken up at the bottom, which you want to have as much space as possible in your robot to just allow for other mechanisms to work. And there's a lot of moving parts in here, and I think I don't know this for sure, but I think they're using 5 motors for the drive team, and ideally you don't want over like 4 motors for your drivetrain. The drivetrain. I said team. Yeah. Yeah. So I don't know. It's just kind of bulky. It might break because there's a lot of moving parts, and yeah, it's kind of sketchy. Although it's cool to look at, I don't see this performing very well during a competition. It's kind of tricky to get around the bulkiness of it. So yeah, although it's cool, I don't see it working out too well. So yeah. Okay, so another way to kind of get an idea for design is looking at FRC and VEX Robotics competition. So if you can see in this picture on the left, this is an FRC robot, and this is called a double reverse 4-bar, the lifting mechanism that they're using. And on the right, this is VEX Robotics competition. The robots are similar to the size that we make. It's similar to FTC in a sense, but the lifting mechanisms are basically the same idea. So I know for sure that in VEX, they use this a lot. They use this type of lifting mechanism a lot. So I'm going to assume that this FRC team used, they saw this and took it as inspiration for their FRC robot. It's not very common to see this type of lifting mechanism, but they decided to go for it since they saw it here and they thought, wow, this is a cool idea. Let's do that. Oh yeah, so so Ultimate Goal is a shooting game. However, you're not shooting balls, you're shooting rings. And there was an FRC game. I don't remember the year it was from, but it's called FRC Ultimate Ascent. And essentially they had to shoot frisbees. So frisbees are flat, just like our rings are flat. So maybe you could look at robots from FRC from this game and gain more inspiration of how they were able to shoot the frisbees, because it's similar shape to the rings that we have for this game. So yeah. Okay, so we have 3D printing, right? So sometimes you'll want to 3D print something custom for your robot, and we basically, well, obviously, we 3D print that. So the reason why you would 3D print something is if you have a part that's kind of a weird shape and you can't really replicate that shape without 3D printing it, okay? So this claw, for example, has like a specific like shape to the grippers right here. So yeah, the reason why you would instead of, I don't know, using wood or metal, it's easier to be more precise with the shape that you're making using 3D printing. Also, you don't want your 3D print to be huge. It takes a long time the bigger the print, and it's more plastic. So yeah, usually 3D prints are small things. So the type of 3D printers we have are called FDM 3D printers, or fused deposition modeling. So basically this means that strings of plastic are being stacked on each other layer by layer, as you can see in this GIF. There's a different type of 3D printing called SLA, but I'm not going to get into that. It's different and kind of dangerous, and it's expensive. So yeah, just so you know. Well, so how do I 3D print something? All right. A lot of people in the interest forums said they wanted to 3D print things. However, they didn't want to CAD, which I thought was interesting. So I guess you guys didn't understand that there is a connection. Oops. Okay. You guys didn't see a connection. So basically, you need to know how to CAD in order to 3D print things, because obviously you need to CAD your custom model first in a software. And then, in order to actually start 3D printing it, you have to import that CAD file into a slicer software. So a slicer software essentially translates the 3D model into this thing called G-code. And G-code is basically the instructions for the 3D printer to understand how to recreate it with code, because obviously it's like a machine. It needs code to do things. So yeah, and then after you exported your G-code, you have to put it on a USB flash drive or an SD card, and then you put the SD card in a printer and then press the buttons on the printer, and then it starts printing. So yeah, those are just kind of the steps on how 3D printing works. Keep tolerances in mind. So basically, in real life, things aren't perfect, but in the software, it is perfect. So you have to account for the way things work in real life. So let's say, for example, you wanted to have a part with, most of your parts are going to have holes in them for screws to go into, so you can attach that part to your robot. And these holes are going to be super small. And usually, because 3D printing involves melting plastic and cooling it down, as the plastic cools down, it actually expands a little bit. So your hole that you made might actually be smaller than what you intended it to be. So in your CAD software, you have to keep in mind, you have to add a little bit more to make the hole a little bit bigger to account for that expansion. So yeah, just a quick tip. It's very important so that you know your 3D printed part is going to be the way you want it to. Laser cutting and CNC milling. So this is also another tool we use to make things for robots. Laser cutting is basically you have a flat piece of a panel. It's usually wood, acrylic, or polycarbonate, and it's flat. It's two-dimensional, and all it does is cut out the shapes that you wanted it. You also need to know how to CAD for this as well. You need to plan that out beforehand. So yeah, laser cutting. Yeah, I basically just explained it. It's just 2D. So I said that there's acrylic and polycarbonate, and there's a difference between these materials that I didn't know this until my sophomore year, I think. But yeah, there is a difference between these materials. They look the same. They're both a clear plasticky sheet, but yeah, there's a difference. So you can choose which is best for your application. So polycarbonate is more bendy, and it's less likely to crack. So if this thing is going to be moving around a lot, then you would want to use polycarbonate, so it's less likely to break. Acrylic, on the other hand, is rigid and it's more likely to crack. So acrylic is more stiff. It's kind of like glass in a sense. So I don't know. It just depends on what you're making. CNC milling. So we do not actually have a CNC mill, but basically a CNC mill does the same thing a laser cutter does, except it has the power to cut metal. Because a laser cutter is not strong enough to melt metal, that's ridiculous. It doesn't work. So yeah, I just wanted you guys to know that. Oh, other teams can CNC mill. They do that. So yeah, as you can see in this picture on the top over here, this robot is completely made out of wood. because they were able to laser cut all this wood. So, you know, it's completely possible to do so. Pretty awesome, I think, in my opinion. Yeah. So, this picture on the bottom here, I can clearly tell that their chassis on the side I'm circling is made out of metal, simply because there's like triangles in the chassis. So the reason why they make triangles is because metal is heavy, so they want to be as light as possible, so that's why they have holes. So that's how I can tell it's metal, and they use the CNC to do it because it's very clean. It's kind of hard to see, but this panel with their team number on it is either acrylic or polycarbonate. I can't tell you which is which by just seeing it, but yeah, usually polycarbonate or acrylic is used for a side panel for decoration. So yeah, just so you know. Okay, CAD software. We're actually going to get into the CAD portion after this. So I just like to explain that in the classroom, if we were at school in real life, we would still be using Autodesk Inventor. However, we have to switch to Onshape simply because not everybody has their own PC, and we wanted to be inclusive of people who don't. So Onshape can run in a browser, so you could run Onshape on your Chromebook. So that's why we decided to go with Onshape, because wow, everyone can CAD now. So yeah. So is it better? I personally, I prefer Inventor simply because I'm used to Inventor. Okay, Onshape is pretty new to all of us. It does the same things that Inventor does. However, things are in different spots. It just kind of takes a while to get used to for myself. And this is also another plus to Onshape. You could have multiplayer CAD. It's easier to share CAD files with other people, and you could actually be working on the same document or the same part with someone else at the same time, and you guys can see your changes like happening in real time. So that's a cool thing about Onshape. I think the only con with Onshape is that it does get pretty laggy. I don't expect much from it since it runs in a web browser. So yeah, it does get kind of laggy at times, especially when your assembly is really big. There's a lot of parts going on. So yeah, that's just a little con. So well, why do we CAD? What's the point of CAD? CAD is actually extremely important, and this is why I actually kind of like the situation we're in right now, because we're actually we have to CAD before we build now. We're forced to CAD before we build. In the past, a lot of us would just start building a robot with no plan. We just do whatever, and that usually turns out bad because we figure out that things don't fit the way we intended them to. And it just gets kind of messy when you start building things without a clear plan. So basically CAD is for, I guess, making a blueprint for your robot in a sense. So you basically like build your whole robot beforehand, except it's virtual. So that's very cool. Yeah, that's pretty much it for this presentation. Now I'm going to go into the Onshape software. But first I'd like to show off a robot. Why does it hate me? Okay, let me just refresh. Please. Okay, yeah. It's loading. See, it takes a while sometimes. This is a whole robot, so yeah. Oh, I just like to say that I didn't make this. Another team was kind enough to share this with me so I could show you guys. So that was pretty cool of them. But yeah, this is their robot CAD. Why is it? Okay. But yeah, this is a robot CAD from last year. Why is it it hates me. Let me just exit out. Please. Why did it break? Is it because I'm Can I open another document? Wow, we love technical difficulties. Okay, real quick, let me just like stop recording. You guys can see it, right? Yeah. Okay. Oh, as I was saying, yeah, this is an example of like a fully fledged robot. It's completely done. All they had to do was copy the CAD and build it in real life. But yeah, it's pretty cool. Yeah, like I said, I didn't make this. Another team shared their CAD with me. Yeah, pretty cool stuff. It does get kind of laggy since it's there's a lot of tiny parts going. There's a lot of stuff going on. And as I said, Onshape is not perfect. Like I never had that issue before. I don't know. Maybe it was being weird because I was sharing my screen in Google Meet. But yeah, the cool thing about Onshape is that your constraints will actually kind of like work the way you want them to. Now, Onshape is laggy, like I said before, so I want to try to show you guys. Like this actually extends upwards, so I want to try to do that. It's very finicky. I don't know. It's kind of whack. Please, it looks really cool. Yeah. Okay. So yeah, it goes really tall. I could make it go even more. In fact, maybe. Yeah. Okay. See. So yeah, pretty cool. You know, you can make it work how it should. So yeah, I'm gonna go over how to make a basic part. This is just very bare minimum. Something you just really need to know this. So yeah, I went over here and pressed the create button, and everything you make it Onshape is called a document. Just so you know. I'm gonna name this intro. Sure. All right. So uh, when you're CADing things, usually everything starts out as two-dimensional. So the first thing you do is a sketch. So I click the sketch button. Now it's asking me to select a plane. So there's the X, Y, and Z axis. That definition is a variable. It doesn't really matter. Personally, I prefer to use, it's called top. I like this one because it almost simulates like the ground, right? It's kind of like you're building up. So that's why I like to use this plane personally. So I clicked on that plane and now it's showing me, oh wow, I have a sketch created. It says right there. So I'm gonna change my view so that I'm looking at it from above. Yeah. Oh, also, if you decide to CAD, you definitely are gonna need to use an actual mouse because this sucks with the trackpad. I'm just saying. But yeah. So I want to make a cube. Okay. So I'm going to start off with the rectangle tool, and a lot of the things you make are going to be based around the rectangle tool. Pretty simple. There's two types. There's a corner rectangle and the center point rectangle. I'll show you the difference right now. So I have the corner rectangle selected. It's pretty self-explanatory. You click a corner and then you can extend it out to a corner. Yeah, there you go. And I'll show you the center point rectangle. So basically this kind of acts like the way a circle would. So it kind of extends out from the center like a circle radius type of thing. So yeah, I'm just gonna use the corner rectangle right now. So yeah, I'm just gonna make a cube. So I'm just gonna randomly just click. Okay, cool. We have a rectangle looking thing, but I want this to be, a perfect square. So most of the time, you're going to need to be using the dimension tool. Okay, everything you CAD needs to have a specific dimension associated with it, because obviously that's just common sense. Like you want your part to be a specific size. Let's just say I want this to be 2 inches high. Yeah, so I just selected an edge and it changed the dimension of that edge. And I have to do this other side as well and make it 2 inches. So now I have a square. So that's cool. It's done. I sketched a square. I'm good to go. So just a check mark. And so now it kind of exits out of sketching mode, and now we're kind of in 3D mode, I guess you could call it. So what I'm going to do is change my view so I could actually see what's going on in 3 dimensions. So this is also another tool you're going to use a lot. It's called the Extrude Tool. So basically all it does is I selected it, and all I have to do is select the sketch that I made, and it kind of extrudes it out. It extrudes it upwards. This little black arrow right here, all it does is make it extrude the other way. Yeah, it's called opposite direction. Wow, obviously. So yeah. So I wanted to make a perfect cube. So my depth has to be also 2 inches. And yeah. Oh, also when you're changing the numbers here, in order to see the updates, like I just typed 1, I have to like click within the window and then it'll update. So yeah, just so you know that. So yeah, wow, now I have my cube. Cute, wow, nothing too crazy. Now I'm going to show you a few tools to kind of, make your cube a little fancy. The first one we have is called the fillet tool. So basically what this does is just round off edges. That's also pretty self-explanatory. I can drag this arrow to change how round I want it to be. Oh, wow, that's interesting. You could also change the numbers if you have like a specific, I don't know, rounded edge you want. Okay, now we have the chamfer tool. It's the same idea, except it just flattens that edge instead of curving it. Yeah, that's pretty much it for the chamfer tool. Draft tool. So what the draft tool does is you have to select a face on your part. And what it does is, let's see. I don't use this often. Hold on, I'm trying to figure it out too as we speak. Oh yeah, what if I change a number? 45? Let's see, what does that do? Okay, yeah. As I said, I'm like new to Onshape as well. Okay, like I just learned this kind of like a week ago, and I'm not familiar with everything quite yet. Basically, if the draft tool, I guess I can't, I don't know. Onshape is very picky with what you do. Basically, it just adds like a triangle onto that face. So you could change the degrees. Wow, it's like a slanted house or something. Looks like a roof. I don't know. Yeah, that's the draft tool. I'm not too familiar with rib, so I'm not going to go over that yet. But shell tool basically hollows out the part. So I selected this face, and basically it just removed that entire face and then made the inside of the cube hollow. So it's almost like a little box. I could also change the thickness of like the walls of the box. So let me make it like, half an inch. And wow, it's like thick now. Yeah. Also, I could make the box hollow, so I could enclose it essentially. It doesn't look like anything happened. It just looks like the normal cube, but it's actually hollow on the inside. So yeah. Okay, yeah, we have the hole tool. Personally, I don't like to use a hole tool. I like to make my holes in a sketch instead and extrude them. But basically what how to use a hole tool is you need to make a sketch and place a point somewhere. And I'll confirm that. And then with the hole tool, I select the hole tool. And then I select that point I made. And then, yeah, it'll turn it into a hole, which is pretty cool. I think you could like do like some fancy stuff with it. Counter bore, what is that? Okay, yeah, so then it just creates more space around that hole. Maybe you have a screw and you want the screw to be inside there so it's flush. Stuff like that. You can specify countersink. Okay, yeah. Yeah, that makes it like a cone on this. Yeah, it kind of makes the hole a gradual thing, I guess. So yeah, that's the hole tool. So now I'm gonna try to make a Lego piece. And then once I make that Lego piece, I'm actually gonna show you guys an assembly of connecting those Lego pieces, because you guys are going to be using assemblies a lot, right? This entire robot is an assembly. Assemblies are very important. That's probably what you're going to be doing the most is making assemblies. So yeah, I'm going to make a Lego piece to put into an assembly. So let's get into that. So yeah, I have my cube here, but it doesn't look like a Lego yet, right? It's usually Legos are rectangular. So I can actually go in and edit the size of this. So on the side over here, it has all of the things that I've changed. So I have like, oh, this is my sketch for the point I made. In fact, I don't need that. I could delete it. So yeah, this is the original sketch that I selected. So if I just double click that, it'll take me back to the sketch as if it were like default, or as if I were to like already, as if I were to make it like, whatever. Yeah, so it takes me back into the sketch. So I can actually double click on the dimensions and change the size of it. So I'm gonna make this 4 inches now, so it's a rectangle. So I'm gonna confirm that, okay, I'm done. And then it automatically extrudes it back up, but it's now a rectangular prism instead of a cube. So that's pretty cool. So usually Legos have, you know, the studs on the top, the round studs. So I'm actually gonna do that. You need to make another sketch. And then this time I'm going to select the top of my Lego as like the plane, or it's like the face that you're going to be sketching on. So yeah, so I selected it. So I'm gonna make a circle for the stud, and Legos have 2, depending on the size. And remember, I still need to dimension them. So I'm gonna give it a diameter of, let's say 1. Yeah. Oh, also it kind of, because they're like linked, it's on the same sketch, so it kind of scales them both up at the same time. You don't really need to worry about that. I just have to go in on this other one and also make it 1 inch, and then they're both the same size. So obviously they're just kind of in random places. So I need to, you know, specify where I want this to be on my part. So like I said, you're going to be using the dimension tool a lot. So I'm actually going to select the center of the circle, and then the edge, I want to specify how far it is from this edge. So I'm going to, I don't know, make it 1 inch. And then that side, it's constrained to be this distance. However, I could still move it up and down. It's just not in the place I want it to be specifically. So I'm going to also dimension it from this side and make it also 1. So now it's more centered. You'll also notice that it turned black. That means it's like fully dimensioned. It's not going to move anywhere. This one can still move. It's just like you never specified where it should be. So I'm going to do the same thing I did for this one. One inch. Okay, yeah. So now they're in a decent spots. This is where I want them to be. I'm gonna confirm this. And yeah, so you can see the sketches. So I'm gonna extrude them now, just like I did with the original cube. Same idea. Oh, a cool thing about about extruding is you could also choose like this, right? You can make holes like this. I don't want to do that, but I just thought it's like a cool thing to note. Like, wow, interesting. Anyways, I want to extrude the studs. And I also want them to be, these look too tall, I'm gonna make them 1/2 inch. Okay, cool. So it's starting to take shape, looks like a Lego. But obviously Legos also have holes on the bottom, so you can interlock the Legos. So let me just do that. It's basically the same idea of what I just did with these, except I'm going to be making them a hole, like making a hole instead of adding them. So I'll show you that in a second. So I'm gonna make another sketch, like I did before. 2 circles, nothing crazy, 2 circles. Dimension them, 1 inch, 1 inch. Oh, I accidentally made that too. Okay. And then I'm going to specify where they should be. Dimension, which should also be 1 inch. And then cool. Other side. Okay, cool. So we have like the same idea as what we did with the top. I'm gonna confirm this, and then I'm going to extrude and select these two holes. So obviously it's gonna think it wants to go out. However, if you look in this window over here, you can press remove. So that changes it from adding to remove or subtracting from the part. Okay, it's like making a hole. And just like these studs, they're 1/2 inch, I'm going to make this hole 1/2 inch. So wow, the Lego's done. So now I'm gonna go into making an assembly with these Legos. So, okay, yeah, this tab at the bottom is basically your entire workspace. So the more parts you add, the more tabs there'll be. So every document by default comes with a part studio and an assembly. So yeah, I just went to the assembly and I'm going to click insert over here. And it shows up the parts that are in the workspace by default. Like, wow, my Lego is right here. I just have to click it and I can move it around and then click again to confirm that it's there. I could also add a second one like this. So that's cool. You could also copy and paste as you would, Control C, Control V. Yeah, so that also works, but I don't need that one, so I'll just delete it. You can also delete things by just pressing backspace, which is cool. Wait. Yeah, okay, it's just being laggy. So yeah, so basically what we want to do is stack these as you would, kind of like this, but like they're just kind of floating around randomly in space. So you need to give these pieces some constraints to make sure that they stay in the places that they have to be in. So first, I'd like to recommend that you fix one of the pieces. What fixing means is that I can't move this around anymore. It's frozen. I can still move this one, but this one's frozen. Okay. Okay, like I said, I'm pretty new to Onshape, so there's a bunch of like different constraints that I'm not entirely sure what each one does. However, for this case, I'm going to be using the cylindrical mate. So basically what that does is we're working with cylinders here, right? So it just makes sense. Basically all I have to do is select this cylinder and then go to the hole over here, and it's also like a cylinder, right? And then I just click them and then press the check mark, and wow, it looks like it's all coming together. Looks great. But also I'm not finished here, okay? Just because it looks like it should be where it is. I like to call this the shake test. I could still move it around, okay? We don't want that. I can still move it up and down, and it also rotates. So I'm actually going to use the cylindrical mate again, just for this side, so that it kind of locks in. We'll just do that again real quick, please. Yeah, okay. You also need to be like really particular with like where you click, because it can change like the way the constraint works. So yeah, okay, looks good. I think I could still move it up and down, and I don't want that. I want them to just stick together. So to fix that, I'm going to be using the Planar Mate. Essentially what this does is it glues two faces together in a sense, right? I'll just show you real quick. So I just select this face, and then I'm gonna select the bottom of this, and then wow, it glues them together. And then it passes the shake test. Okay, nothing's moving around anymore. If I unfix the original, I should be able to move, yeah, the entire thing around without it falling apart. It's also being really laggy because Onshape is laggy. But yeah, that's just basic assembly stuff. I don't really have anything else to show you other than the fact that there's a lot more things you can do with Onshape. It's just that I myself am new to it. So, I mean, most of robotics is teaching yourself or self-learning anyways. So I'd highly recommend that you guys make an account and start messing around for yourselves. Try to copy what I did maybe. I don't know. You could do whatever you want. But yeah, that's pretty much all I have for y'all. So yeah, I'm done.